So basically, we've already studied about how to get the number of protons and electrons and neutrons in an atom. However, in order to understand chemical reactions, we're going to have to understand a little bit about where the electrons are and where they belong, where they're filled, what orbits they're in. And so in order to do that, we have to study electron configuration. And this is the second half of the chapter 9. The very first thing that we have to understand is that an electron is a negative particle, and it is not in the nucleus, but it's around the outside of the nucleus. So it's in some kind of an orbit. And the very first thing we sometimes think about is that here's the nucleus, positive, and neutrons, and we see an electron going into orbit. Okay? Well, what we have to realize is these electrons' orbits are three-dimensional. So if I have an electron going in a circle, it's actually a sphere that it's making. So the electrons in the periodic chart are actually what causes the element to have a certain kind of chemical behavior. For instance, sodium becomes +1 because it gives away an electron. Chlorine becomes -1 because it accepts an electron. All chemical reactions are the transfer of electrons. So we're going to begin by trying to understand how the electrons are arranged and why they are given away or accepted. So let's start with the simplest element. And that element is hydrogen. It's in row 1. Okay? Row 1. And it's hydrogen. And hydrogen has, an atomic number of 1. So it has 1 electron when it's neutral. And it has 1 proton. So we picture hydrogen as having 1 positive proton in the middle and 1 electron going around it, negative. That electron is going around it in what we call the first shell. The first shell. And shell is a certain average distance from the nucleus. So the first shell, the electron is very happy. It's pretty close to the nucleus, and it's going around in a spherical orbit. And the spherical orbit has the shape, it's called a subshell, and it's called S, and it's a sphere. So you might envision hydrogen as simply being the inner circle here that's in pink, a sphere, a small sphere. This happens to be a picture of the orbitals. The s orbitals are spherical, okay, and it's a subshell. All of the elements in row 1 have only 1 shell, the first shell. If we move to row 2 to lithium, then we have a different situation. Lithium's atomic number is 3, which means it has 3 protons in the nucleus and 3 electrons. So right now we're interested in the number of electrons and how they're arranged in the atom. Well, this tells you that here's the +3 nucleus, and it tells the first shell is filled with 2 electrons, 1, 2, because there's only 2 things. So there are 2 electrons in the first shell. But then when you're in row 2, you come to the second shell. And I have 2 electrons in the first shell. I'll have put the 3rd electron in the second shell. So very simply, this could be a lithium atom with 2 electrons in the first shell, S shell, in the subshell, S, is filled with 2 electrons. Then we move then to the 2s, the second shell, and its subshell S, spherical, and it can have two, but lithium only got one. So we could write the electron configuration is of lithium in the first shell. That's the same as the row. In the S, there are 2 electrons. Then in the second shell, in the S, there's 1. And that's the electron configuration for lithium. 1s, 2 electrons in the first shell, and 1 electron. Altogether, 3 electrons. Okay? Now what happens in the second level is interesting. Remember that the shell gives you the average distance. Well, for a sphere, the distance is constant from the nucleus. But there's another kind of subshell in the second level. And that second level is, it has what we call the p orbital. So these are a set of orbitals called the 2p orbitals. And let's take a look at them. And I wanted to show you the model because sometimes the picture is hard. The P is sort of shaped like a dumbbell. Now you can see that if electrons in here going back and forth, kind of in a figure 8 shape, you'll sort of be going like this. On the average, distance is the same as the S. So in the second shell, the average distance of the electron is the same as this, but it's moving at a different angular momentum. Now, these are the p orbitals. The p orbitals are shaped like a dumbbell, and there are 3 of them. And they have names, because if you think of 3 dimensions, you have the y vertical axis, you have the horizontal axis, and you have this axis y. You have the x, y, z in 3 dimensions. So this is the py, this is the px, and this is the pz. Now every subshell or orbital can have 2 electrons. So since we have 3 p orbitals, that means we can have 6 electrons in those p orbitals. Let's take a look at what that shows us on the periodic chart. On the periodic chart, this is called the S block. The outer electrons are occupied by the s orbitals. Skip these are the d orbitals, and this big block over here is the p orbitals. Okay? And so how many electrons? 1, 2, 3, 4, 5, 6. There can be 6 electrons in the p orbitals. Now let me show you how that would work. Let's take an example. And let's take oxygen, because we look at oxygen and we ask ourselves how many electrons are in oxygen. When we see oxygen, we see its atomic number is 8. So oxygen has 8 electrons. So let's do ourselves a job of putting them in the right place. I'm going to make a convention here, and I'm going to say that the red spheres represent s electrons, because they're a happy little sphere, and the green represents p electrons. So let's start taking them out. And here represents the 1s orbital. So I've put in 2 red dots here, okay? That's filled. That went like this. 1, 2. The first orbital is filled with 2s. Then I move to the second orbital. And I notice that I can put, there's 2 types of orbitals in this second one. One is a sphere and one is the average distance of this. So I'll go ahead and I'll put 2 red s electrons in the second one. I'm going to do it right here. this is a 2, and this is shell 1, shell 2. I'm putting 2 in, and they're s. Now that s orbital is filled with 2 electrons. So now I move to the p electrons, and I can put 2 in each orbital. But so I have no more s's. 2, 4, 6, 8. 2, 4. I can only have 4 more. So now in this s second shell, I have to put the 4 p electrons. Okay, and 4. So I would write this configuration. It would be 1 s 2 electrons, 2 s 2 electrons filled with 2, and then 2 p 4. 4, 5, 6, 7, 8. 8 electrons. So that's the way we write the configuration of the electron configuration for oxygen. Basically, you could also do this by looking at the periodic chart. You can do this by saying, okay, here is oxygen. So let's go ahead and fill this. 1s2, 2s2. And after I get done with that, I come over here to p, 1, 2, 3, 4. I've arrived at oxygen. So the periodic chart will allow you to write the correct electron configuration. Now, I would like for you to know that this is filled. When you reach the end of the first row, that's filled 1s. When you reach the end of the second row, that's filled 2, second shell. But you notice oxygen doesn't reach the end. So what you have to say that this is the outer valence, the NCE elect shell, and it has 6 electrons. So oxygen, 8 electrons, could be divided into 2 in the core inside, and in the outer orbit you end up with 6. Now this is a pretty simple molecule. You also could ask yourself, why does oxygen like to have a -2 valence? Why does it like to pick up 2 electrons? Well, it's very easy to see that it's lacking 2 in being filled in the second level. You can look at the periodic chart. If you go over to neon, you've added 2 electrons. And so oxygen likes to add the 2 electrons and have the filled orbitals of the second level. Let's take a substance like magnesium and start from scratch. Magnesium has how many electrons? Well, we looked at the periodic chart, 12. Has 12 electrons. Can we do it correctly? Well, the filling order is the same as the periodic chart. So we'll start up here in the first row and fill the S. So it's going to be 1 shell S, and it's going to put 2 in there. Then the next one, when we move down to the second row, we have 2 S, and we can put 2 in there. Then I come over to here. I'm still in the second level, right? And I have now 2p, and I fill that up. 1, 2, 3, 4, 5, 6, 2p6, and I'm going to magnesium. And I get down here, I'm on 3s2, and that's it. I would identify this group. This is the filled orbital, this is the core, and this is the valence. How many valence electrons does magnesium have? It has 2. And it would like to get rid of them, because if it got rid of them, you'd be setting with the filled orbitals. So magnesium tends to have a +2. So writing the electron configuration can be kind of fun, and it's easy to do if you actually use the periodic chart. There are several things in your rules that you might want to look at. You might distinguish between electron configuration and orbital diagram. So let's take the electron configuration of carbon. It's 1s2. Carbon, you can see from periodic chart, has 6 electrons. So carbon, 1s2, 2s2, 2p, and when we get to the 2p, it has 1, 2. Okay? That's the electron configuration of carbon. Carbon has 4 electrons in its valence shell, the outer shell. Now, what we can do here is that we can make boxes. That's a diagram, and this represents the 1s. This represents the 2s. And for the p, we have to make 3 boxes, because there are 3 p orbitals. Remember? Px, py, pz. So I'll label them that way. 2px, 2py, 2pz. And then I start filling them. And an electron like that means an electron spinning one direction. And the rule says you can't put 2 electrons of the same spin in. So the second electron is spinning the other direction, and then that's filled. And you go like that. Okay, I got 4, and remember I have 6 to do for carbon. So I have to put 2 more. Now my question is, where will I put those 2? Well, the rule says that they'll spread out first and then pair up. So I'll have to put 1 here and 1 here. And so the orbital diagram for carbon is that, and this tells you that it has 2 unpaired electrons. It's really not too much consequences, except that when things have unpaired electrons, they're magnetic, or they respond to a magnetic field. And so the distinction between an orbital diagram and an electron configuration. The most important thing that you need to do from this chapter is you have to be able to identify how many electrons are in the valence shell. And you will also notice that that we will sometimes, whenever we have a filled shell, we will sometimes just simply say we're writing an electron for magnesium. We would simply say, a shorthand notation, we'd simply say neon, because when we go back from magnesium, we go back to neon, it takes care of 10 electrons. So neon, 10, and magnesium has 12, and so 3s2. This is a shorthand notation. The core for magnesium is the filled neon, and then this is the valence with 2. So writing electron configuration, just go over one more thing why we're doing all is to understand why the charges of the ions are plus. Everything in here, in this whole column, has 1 electron in its outer shell. And the outer shell is 2s1, it's 3s1, 4s1, 5s1. As you go down, you're just adding a shell, adding a shell. And the same thing over there on this side. Each time you move down, you add a shell, and all of the halogens, if you look at the halogens, they all have 7 valence electrons. There'll be, for instance, fluorine has 2s2, 2p, 1, 2, 3, 4, 5. 2 plus 5 is 7. They all have 7 valence electrons. And they like to have 8 valence electrons in the second shell, so they'll pick up an extra electron. all the halogens will be a -1 ion. I hope that helps you in writing the electron configuration and understanding where they are and why chemical reactions occur, why some things are positive because they want to lose that and have a filled shell, or why some things are negative, they want to pick up extra electrons to get a filled shell. So thank you for this. Good luck.